So, before you came to this class, you had an idea that sodium chloride, kind of had sodium. The metals tend to lose electrons. We've been talking about that. Okay. Actually, as it turns out, there's a certain amount of energy required for that to happen. So in this class, we're all about quantifying things, and we're going to quantify that. Okay. So for sodium to go to a +1 cation, there's a certain amount of energy required in order for that electron to be kicked off. And that's called the ionization energy. Okay. And it's expressed in terms of energy, kilojoules per mole of electrons that were kicked off. Okay? Makes sense? So what we're going to see with sodium and metals in general is their ionization energy is pretty low. Why? Because they don't have to work too hard to kick off an electron or 2 or 3, depending upon what sort of cation they tend to want to form anyway. Okay? So the lower the ionization energy, the more friendly it is for that species to kick off an electron, which is what ionization is. Okay. So the more it tends to want to form a cation anyway. So this is all, I like when things are consistent. So this is all kind of consistent with what we've been talking about with regard to what has low ionization energies are going to be the metals, because they want to kick off electron or 2 or 3. And remember, why they want to do that is get like the rare gas in the period before them. Okay. Conversely, the nonmetals, those are kind of those select few that are on the other side of the jag, those tend to want to form anions. Okay? These tend to want to bring in electrons. So giving up an electron kind of goes counter against what they want to do. So they have really high ionization energies. I like it. So here we have some arrows again. If we're just focusing on the group A elements, so that's S block and P block, forget the B and the B's, which would be what, D and F block. We have this trend now. So ionization energy gets harder and harder to kick off an electron as you go across the period. And that kind of makes sense because you're getting closer to the nonmetals who don't want to kick off electrons.
And you're getting closer to your valence electrons.
Yeah, you're getting more and more valence electrons. Exactly. Yep. And if you're in the same period, same group, if you're in the same group, it increases as you go up. Okay? So, like, I'm looking at the periodic table. I'm going to ignore the group AA for now, if that's okay with you, because they don't like to gain electrons or lose electrons. So starting with fluorine, that's like the tippy top of the ionization energy. Okay, so fluorine, it'd be really hard to take off an electron. All right. So, is it hard to take off an electron, high ionization energy, or is it easy to take off an electron, low ionization energy? Well, in a sense, it does kind of trend with atomic size a little bit. So remember the way an atom is structured is basically we have this nucleus and you have electrons outside. Now, the fluffier the atom, the farther away that valence electron or electrons are from the nucleus. So actually, that's kind of why, as we look at the group 1A, which is what these guys are, okay, we said the size of the atom gets bigger as you go down, okay, and that's why, kind of related to that, as you go down, the electron is farther and farther away. So ionization energy is less. So it's easier to kick it off. Remember, when this is lower, it's easier to kick it off. Okay, so that's how that kind of goes. So this is kind of like a table or a graph we looked at the other day where you recognize your rare gases and think of them as marking the end of a period. So here we have period 1, period 2, 3, 4, 5, oops. Yeah, 6. Okay. So you can kind of see how ionization energy gets, I'll pick on period 2. Ionization energy gets more higher and higher and higher. Okay, and then here we are at the 1A element, ionization energy increases, ionization energy increases, okay? So, as you get closer to the rare gas. And here's bars showing the same thing. So the taller the bar, the greater the ionization energy. And again, this is just picking on the S block and the P block, just picking on the group A elements. So aluminum kind of does something a little funky. Silver, boron, but in general, you kind of see that trend. So, and this might have been one of the things that, bless you. Your name? I can't think of your name.
Me?
Yeah?
Joshua.
Joshua. I know. It's like my mind is gone. I got up this morning, I'm like, is it time? Do I really have to go to school? So anyway, this is kind of like what Joshua was saying about the valence electrons. Okay, so this is what we have going on in our period 2 elements. Okay, so again, valence electrons look like they're all in n is equal to 2. Okay, so here we have 1 valence electron, lithium 1A, 2 valence electrons, 3 valence electrons. Carbon's got 4 valence electrons, 5 for nitrogen and 6 for oxygen. Don't know why we didn't put fluorine on there, but that's okay. You get the idea. So the ionization energy increases as you go down. Okay, it gets harder and harder to kick off an electron because they kind of want to keep their electrons and actually pick up more electrons, become anions. Okay. So now it's possible, once you form something into a +1 cation, okay, it's possible to kick off another electron. The first time you kick off an electron is called the first ionization energy. Okay. The second time you kick off an electron is called the second ionization energy. Okay. And we know that happens. My goodness, if you look at the 2A elements, heavens Betsy, they just want to kick off 2 electrons. Okay. And if we go over to aluminum, gallium, indium, and thallium, we're talking about +3 cations. They want to kick off 3 electrons. So there would be actually 3 different energies. And the energies are not the same. So the first electron goes most easily, followed by the second, followed by the third, followed by the fourth, if there is one. Okay. So it gets increasingly more difficult to take off an electron. And this kind of makes sense because you figure 2 things happen. If you kick off an electron, then actually you kind of have a more of a lopsided positively charged protons, and so those electrons that are left are going to be snugging in. Okay, if you kick off an electron, we talked about cations are smaller than their parent atom, so the thing becomes smaller, they're closer to the nucleus. Okay, they have more of an attraction there. So, oops. So that's why I brought this book right here. So one of my tabs, I think it's this last one right here, it says ionization energies. So I don't know if I'll pass this around, but right here we have atomic number, and it goes up to silver, 47, okay? And actually this looks like 21, we're moving 21 electrons, yeah? So each of these this is the first ionization energy, second ionization energy, third ionization energy, okay, for these elements. And it looks like it continues down here. I guess I won't pass this around. But, oh, it stops. No, those are potentials.
What happened to the pages? Why are the pages pinkish?
Why are the pages
What
what?
happened? Like, the pages look a little discolored. What happened?
Yeah, the pages are discolored because of my candle. Yep, that's all it is. And they're discolored, it wicked in. Just kind of migrated in. Anyway, that's what I was going to show you for that. And I tried again for the whole movie thing, because these videos actually would help. I'm just going to kind of walk you through what happens with magnesium, what the videos would have done. I don't know why my videos finally just stopped working this semester. on all my equipment. So if we are going to take a neutral magnesium atom, that's what this little equation is showing you, neutral magnesium atom, how do we know it's neutral? There's no charge up there. And we are going to zap it with energy. I'll go ahead and for the energy I'm going to put, let's see, I think I'll put IE number 1, first ionization energy. Then what are we going to have left? Well, on the product side, we're going to end up with a +1 cation and one electron, or 1 mole of electrons probably. Okay. So the new electron configuration is, if this is Mg, I bet you by this, Mg +1 is going to be 1s2, 2s2, 2p6, 3s1, right? Does that sound right? Yeah, it loses 1 electron. Now, we talked before that magnesium is going to lose 2 electrons. And so this feels kind of weird, right? But it's kind of an intermediate along the way. Okay. So also, I think I mentioned this a minute ago, this guy is going to be smaller, your Mg +1. Going to be smaller than your Mg. Less electrons, electrons kind of hugging the nucleus a little more. Okay. So then let's take it up a notch. Now you see here, this configuration at the top here, that actually is your Mg +1. Okay, notice it peters out with 1 valence electron in the 3s. So now we're going to go ahead and take your Mg +1. We're going to add ionization energy, and I'll call this I period E period 2 because it's the second ionization energy. Why? Because it's already a +1 cation. This is the second go-around. So what are we going to get on the product side? Well, we'll get the +2 cation, which is what we're used to seeing magnesium as. Now I'm going to go up here, and I'm going to say Mg +2. I'm going to write its electron configuration, 1s2, 2s2, 2p6. Are there any in the 3s? No. In fact, we've been talking about that octet. And there's your octet. It has an n-1 or 3-1, or in other words, 2, 2s2, 2p6, right there. And we would say it's happy. Now, and I have numbers here on the last 2 slides from now to tell you how much energy that is. It's more energy, I guarantee you. The second ionization energy is a little more energy than the first ionization energy, just a little bit harder. But the series of videos goes 1 step further. So notice what we're doing here. We're basically starting with something that's already happy, okay, our magnesium +2 cation. We're zapping it again. So if it's a +2, this is our third go-around. So this actually is I period E period number 3, the third ionization energy. And again, it's going to be higher than the second. And the second was higher than the first. Okay. So if this is Mg +2, do you guys buy this? Mg +3, I know, it makes you want to giggle. We said that it's going to go from the electrons will leave from the highest L, and P's have an L value of what, 1, and S's have an L value of 0. So the electron that's going to go is one of these 6. So I'm going to rewrite this electron configuration here, and it's going to go 1s2, 2s2, and now it's 2p5. An Mg +3 cation. Voila! It will be even smaller than the parent cation that it came from. Why? Because it lost 1 more electron even. And the remaining electrons are drawn even more closely to the positively charged nucleus. Cool. Well, so here is the first ionization energy, the second ionization energy, and the third ionization energy. Can someone kind of articulate, if you see, I'm going to go ahead and draw a break there between the Mg +2 being formed. and the Mg+3 being formed. Does that maybe look kind of drastic to you? It's like,
Huge jump.
yeah, the huge jump. What do you think? How would you tell somebody why that's such a huge jump from an Mg+2 to an Mg+3? It had a full octet? Is that what you said? Yep. I think that would do it. This guy right here, Mg+2, already had a full octet. And then to make that jump to an Mg+3, it's unstable. Okay. Going the wrong direction. And that break, that kind of break between the cation it wants to form and be left alone with to the cation it's forced to form, actually that break can be seen in all of the ionization energies for a given species. So you kind of see the break there. So for instance, sodium 1A, magnesium 2A, aluminum 3A, silicon 4A, phosphorus 5A, sulfur 6A. Okay, and you can kind of see the jump between kicking off electrons. Okay, so that's kind of exactly what you said. So the homework, one of the homework that's going to be due, that you got to do over Thanksgiving, actually kind of, we take it for granted that, take sodium chloride, that sodium's going to kick off an electron and chlorine's going to take in an electron. We just take that for granted. But actually we can look at that example, sodium chloride being formed from sodium and chlorine, stepwise and kind of add those energies together like we've done Hess's law. So kind of this little look at ionization energy, kicking off electrons, what metals do, is not just a meaningless task. It's actually a part of something bigger. Okay, all right. So, kind of the yin and the yang. So we said metals lose electrons, and that's always going to take energy to kick off electrons. Okay, ionization energy. And nonmetals pick up electrons to get a complete octet. So there's this thing, and it doesn't just apply to nonmetals, but to anything, electron affinity, I get it mixed up with electronegativity sometimes. But electronegativity is when you have two atoms that are bonded together and you're looking at that tug of war for electrons. Electron affinity is sort of like that, but you're just taking an atom or something, could be something already charged all by itself, and you're dumping electrons onto it. So if you have an affinity for chocolate, such as I do, that means you're like, bring it on. And if you have an affinity for electrons, like, bring it on. Okay, so electron affinity is kind of a measure of an atom's want for electrons. So if something wants electrons, okay, then it is going to form an anion. Something wants electrons, it wants to form an anion. If you chant it to yourself, wants electrons, has infinity, high affinity for electrons, it wants to form an anion. And who wants to do that? Well, it's the nonmetals, okay? Now we have kind of a subtle thing, again, that's consistent with what we've been talking about with positive and negative energies. Like, how does that go? Well, your enthalpies, your Qs, we said that if something has a negative, we said if something is exothermic, okay? If something is exothermic, it has a negative energy change. Our delta H's are negative, our Q's are negative, okay? So this is totally exothermic. And so we kind of have a sort of deal where we're changing gears from ionization energy. You always have to kick in a little bit of energy in order to kick an electron off. But it's quite possible that when electrons are added, energy is released. Okay, so that's exothermic. Endothermic would be when actually you have to put energy in order for the thing to accept electrons, become more negatively charged. In that case, your electron affinity will be positive. So this is, I don't think it's really counterintuitive, but the more negative the electron affinity number, the more energy is going to be released, and kind of the happier or more stable the thing that's formed is. So the second one is endothermic. Endothermic positive, exothermic negative. Cool. So again, just gathering the S groups, the main group elements, the S block and the P block, the A elements, I should say. We have electron affinity increases across the period from left to right, and electron affinity increases as you go up the group. Now, when I say electron affinity increases, the affinity itself increases, which actually could be more of a negative value, okay, because it's more negative, it's more releasing more energy, okay, so that's the one kind of catch with this whole thing. It's hard to explain to somebody who hasn't already wrestled with delta H's being negative, exothermic, delta H's being positive, endothermic. So, but it is consistent with what we've already talked about. Which I like that. Okay. Okay, so this slide is kind of analogous to the ionization energy. A minute ago I said low ionization energy means that the atom wants to become a cation. High electron affinities, which means kind of negative-ish, means that an atom wants to become an anion. Okay. And who wants to become an anion? It's the nonmetals. So hopefully by now, if you're picturing a periodic table, you're kind of thinking the 1A plus 1, the 2A plus 2, the 3A metals plus 3. And then the halogens minus 1, the 6A minus 2, the 5A minus 3. And they will have the highest electron affinities, the most negative. Okay, so I think this is like a repeat slide. Not sure if I had this in here twice, but okay, so the more negative it is, the more favorable it is. Okay, I think we're all on the same page there. So kind of the tipsy, not endo, not exothermic, pretty much neutral, that would be electron affinity of 0. Okay. Notice that I've gone ahead and used the change in enthalpy associated with this criteria. So delta HEA means change in enthalpy associated with electron affinity. The more negative it is, the more positive, the more of an affinity that atom has. So finally, here are some electron affinity values. And if you're like me, you're like, and I'm like, is that right? But there's definitely not the pure trend that we saw with size, and even less of a trend. We saw some exceptions with ionization energy. There's even more exceptions here. That's a little bit topsy-turvy. So I don't think I would give you a test question and have you say, because the trend is increasing electron affinity from left to right, you can't hang your hat on it. Like, look at this. Pick the period 2 with lithium, beryllium, boron. I mean, does it become more and more negative? Well, sort of. Okay. It's definitely not the clear-cut trend we see in atomic size. Cool. So be thinking of these, the way these work, and is instead of kicking off an electron, and kind of think of it this way, because this will help you with your homework. Think of it as basically taking something, neutral atom in this case, something that doesn't have any extra electrons, and adding an extra electron. And then what you get on the product side is that thing with a -1 charge. So think of this. That is.
So will we be asked to take like the mass of lithium and
You could be.
add an electron then figure, to use that to equate the.
That's one of your, I think that's one of your homework problems, is these are all energies per mole of electrons as they're added. And kind of like what Mike's saying is, what if you knew that you had 5 moles of a metal or non-metal that you wanted to dump electrons onto? Okay, so then you would take, if you're dealing with chlorine or something like that, you would take that energy, it would look like this. Is this what you're saying? 5 moles times negative 349.0 kilojoules per mole.
Yeah.
Yeah. And that will give you kilojoules. Does that make sense? Yeah, exactly. You can start to kind of quantify energy that's released during adding electrons. Exactly. So these are the kind of the squirreliness. Remember the trend I told you, and you can just generally do it, but I told you that the electron affinities increase as you go across the period. Sort of. And this is the same thing we saw before. And this is why I said you can kind of hang your hats on, especially including the 7A, that if they're just itching to get that complete octet, and to do that, it's much easier for them to take in 1 or 2 or 3 electrons. So as you go down the group, okay, your electron affinity will, no, across the period, it's like turned around, across the period, your electron affinity in general will increase, the amount of energy released increase. The movie doesn't work. All right, so let's take a look at these and see what they look like. $9.21. I looked at it before. Oh. Wrong folder. Here we go. Okay, so the first one, use principles established to arrange these in order of increasing value of first ionization energies. And then I kind of, over there at the corner, said, remember, ionization energies should, in general, increase as you go across the period and increase as you go up the group. For the second one, I wonder if so for the second one, I said just kind of remember what happened with magnesium when we wanted to go from a magnesium plus 2 cation to a magnesium plus 3 cation. Are there any atoms, well, maybe that doesn't, I guess it doesn't really matter about that break. You could actually answer 22 if you go for the first ionization energy, the second ionization energy, or the third ionization energy. Now that I'm reading the question again, why is it get harder and harder to kick off an electron? And I actually said 2 things. I said actually, as your thing becomes more positively charged, it loses an electron, it becomes smaller. So we have kind of a proximity situation of the electron to the nucleus. And also there's more of a pull for that, bless you, for that set of electrons for that now more still continued, fewer electrons, still the same positively charged nucleus. So something like that. I hate these explain ones. Okay. Some electron affinities are negative, which means energy is released. Some are 0, even positive. Why, then 23 says, why can't you have a 0 or a negative ionization energy? Okay. And in purple here, I said, what do you do with ionization when you're removing electrons? Is it possible to do that? We remove electrons and get energy, and it's reason no. We'll always require energy. That's kind of what I meant for that one. The last one on this set right here, now we get some numbers here. It's talking about sodium, and of course sodium forms a +1 cation. That first ionization energy I wrote down, that 495.8 kilojoules per mole of electrons, that actually is in your textbook. And this kind of goes to a little bit what Mike was saying, that what if you have 1 milligram of gaseous sodium, how much energy are you talking about being required? So my hint in purple here is to, well, first you're going to have to convert the milligrams to grams, I think. And then you're going to use the molar mass to get to moles, and then you recognize that this actually is per 1 mole, and then you can use it in kind of as a ratio. That's that one. Okay. So this, we have a hard time recognizing the difference between BR2 and BR. Maybe you do, maybe you don't. In fact, there's a third thing coming up here, BR minus. Those are 3 different things. If you recognize that in this problem, that will really help you out. BR2 is not the same thing as BR. Okay? In fact, this is what this is saying is it takes 193 kilojoules of energy to take 1 mole of BR2 and break it into 2 BRs. Okay? Well, the problem goes on to say, if you're going to take those BRs that you got from above, and you're going to go ahead and bromine is a nonmetal, actually it's a halogen, it will pick up 1 electron form of Br minus 1. So this is what that looks like. This actually then is describing the enthalpy of electron affinity, right? Okay, so this gets back to kind of the Hess's law process. My hint here simply says add. Now, for me, and I'll go ahead and add to my hints here, I think you're going to have to take this times 2. I think you're going to have to take 2 times 2. If you take that times 2, look what you got. Basically, your BRs cancel out, okay, and you end with your BR2 plus 2 moles of you know what I mean, electrons go to form 2 Br minus 1s. Okay, which actually is your equation of interest. I'll go ahead and finish this. So, equation of interest is this one right here. The formation of Br minus 1 in its gaseous state from Br2. And it's also in its gaseous state. But what it's saying is you have to break it apart first. So my thing is you add this and this. And you should, Hess's law, get your equation of interest. Okay. Okay, another equation of interest. Remember where I said the sodium chloride is it's not complicated necessarily, but we can look at the sodium kicking off an electron, we can look at the chlorine taking in an electron, and kind of get a net energy associated with that formation. That's exactly what's being done here. So instead of sodium chloride, it's magnesium fluoride. So the magnesium is going to form a +2 cation. Actually, that's what's being shown in the first thing, sort of. But notice I think I did it and I thought, well, that's not going to work. You actually have to break this out into 2. So I'll go ahead and fix it. The first ionization energy gives you simply a +1, and then you go ahead and do the second one, and that's an Mg +1. You add ionization energy, this will be the second ionization energy, and then you get your Mg +2, +1 electron. So that's probably how that should have read. So you ionize it twice, and then down here, then you have to do actually 2 of these too. Because because your fluorine is going to pick up, 2 different fluorines are going to pick up 1 electron. So I guess you have that. You can just multiply 3 times 2. And actually, that's my last hint. So let me know if you have any questions, and just wrestle with them and you'll do fine. They're not as complicated as I think I seem to be showing them right now. Okay, that's all I have. Have a great Thanksgiving. Thank you.